Hello and welcome back to Manifolds, the video series where we talk about generalized surfaces and the integration on them. And in that context we have the most important result, known as Stokes' theorem. We have already talked about the general formulation of this result, and in today's part 53 we will start proving it. The proof is actually not too complicated because it's actually quite straightforward. And in order to see that, we will not start with the general manifold, but just with the half space first. Which means that we can just use our knowledge from the ordinary multidimensional integration in Rn. However, before we start with the details, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget that as a Steady supporter or a Patreon member, you can download a lot of additional material with the link in the description. So with that out of the way, let's immediately recall the generalized Stokes theorem for manifolds. More precisely, we have a smooth manifold M with a boundary, and we integrate over M and the boundary of M. Moreover, on the boundary we have a volume form omega, and on the whole manifold we integrate over d omega. And now Stokes' theorem tells us that we have an equality here under the right assumptions. And in fact, there we have two key assumptions. On the one hand, M needs to have an orientation, and on the other side, omega needs to have compact support. So roughly speaking, we cannot stretch the integration to infinity. So the whole integration, left and right, has to happen in a compact set. So this is it. This is Stokes' theorem in the short formulation. Strictly speaking, this formulation is a little bit sloppy because we have different manifolds left and right, but the same form omega involved. Therefore, the formally precise statement would consider the inclusion map of the boundary into M. So perhaps we just call this inclusion map I, so we have a map from del M into M. And obviously there's not much happening, we just send a point P to the same point P in M. Because del M is a subset of M, this is quite a trivial map. But the advantage of this map is that we can easily write down the pullback for differential forms on M. This is what we usually call I star, and it goes from M into del M. More precisely, it takes a differential form on M and sends it to 1 on del M. So what actually happens here is that we have to restrict the tangent space, which has one dimension less in del M than in M. Therefore, the integral over the boundary in Stokes' theorem is correctly understood as the pullback of omega. And this is such a natural definition that we usually completely omit that in the statement of Stokes' theorem. However, now in the proof of Stokes' theorem, it's actually quite important to know that this is happening on the boundary of M. And with that knowledge, I would say we can immediately start with the first step in the proof of Stokes' theorem. And as already mentioned, I don't want to consider general manifolds yet, but to start with the half space, we have denoted by Rn less or equal. We have defined that in part 45, and as you might recall, we set the first component to be less or equal than 0. Therefore, in the three-dimensional picture here, we would cut the space into two parts and we would consider the left-hand side. So we have two directions where it stretches to infinity, and on the third, which is actually the first direction, we cut it. So you see, this is the simplest case of a manifold with boundary, where this whole surface here on the right is the boundary of the manifold. It's two-dimensional, but it also stretches in two directions to infinity. And now we know also in this simple case Stokes' theorem should hold, so let's check that. Now obviously usually you would write down the proof for general n, but here it's helpful to fix it to 3. You will see that we don't need that assumption at all in the proof, but some formulas will be shorter and that's why it's helpful for us. So in that sense, the picture on the right hand side here is actually the correct one. This is our manifold with boundary, and the boundary is this two-dimensional surface. And moreover, you know what we need to consider is an n-1 form omega. This one is defined on M, and you already know that we don't need any complicated charts. we can just use the identity maps. Indeed, this is the advantage of that case. There is no translation needed. We can directly work on the manifold in that case. Therefore, this differential form omega gets p as an input and p has 3 coordinates. And now you see why this restriction to n is equal to 3 is helpful, because in that case omega is just a 2 form. So there are not so many possibilities and we can describe it with 3 component functions. The first component function we can call f1, and then we have dx2 wedge dx3. And then we can have plus f2, where we have dx3 wedge dx1. And then finally the last one with f3. And now important to note here is it's not a problem at all to write down a similar formula for the general case. In that case you would write down a sum symbol and everything looks similar. However, here I want to keep it short by considering the case n is equal to 3. Indeed, it makes it easy when we go to the exterior derivative of omega. So as you know, this one is a volume form on M. And from former videos you should know the general formula to calculate it with the partial derivatives of the component functions. So we start with the first, where we only have the partial derivative with respect to x1. And then, as you might know, we have dx1 wedge dx2 wedge dx3. And the same thing we can do with the next part, where we have the partial derivative of f2 with respect to x2. And then we have dx2 wedge the former 2 form from here. And finally the last term here, where we have the partial derivative of f3 with respect to x3. So this is the whole result, and the only thing that remains to do is to reorder the 2 3 forms here at the end. And there it's not hard to see that they are exactly the same as the one in the front. Indeed, the only thing that could have happened is that there is a sign involved. However, in the proof we will do now, we will see that the sign does not matter anyway. In fact, the important thing we get here is that d omega is an n form, so a volume form on M, and that the component functions from before are put together to a new component function for d omega. Which means the first integral in Stokes' theorem can be calculated by splitting up this component function. This means the integral of d omega can be written as n integrals, so in our case as 3 integrals. And moreover, we can easily translate it to an ordinary volume integral in R3. And again, you should also see it's not a problem at all to do this in Rn as well. And in any case, you should never forget that the first component is always restricted to -infinity to 0. And the other 2 components, as we know, are not restricted at all. Hence what we get here is just a nice ordinary 3-dimensional integral. And as already mentioned, we just have 3 different ones. So this is what we have, and you should know from multidimensional integration that we can just use Fubini's theorem to solve each integral. And indeed, the idea is to do something different in the first integral compared to all the other ones. And this is simply because the first component is special since we cut it at 0. Therefore, we first want to integrate over the first component and then over the others. This means we start by solving a 1-dimensional integral over x1. And then afterwards we can integrate over x2 and x3. So this is the common application of Fubini's theorem. And here the good thing is that this 1-dimensional integral in the inner part is quite easy to solve, because we know that f1 has a compact support. There, please note, this was the assumption, omega has compact support, so all the component functions need to have compact support as well. And this is helpful here, because we can just use the fundamental theorem of calculus for solving the 1-dimensional integral. Roughly speaking, we just need to find the antiderivative with respect to x1. And this is quite clear, it's just f1, where we have to put in the boundary points into the first components. However, since the lower bound is -infinity and we know that we have compact support, we get out 0 for that one. But obviously not for the upper limit, there we have to put in 0. And that's it, this is the result. this is the function we have to integrate over x2 and x3. And at this point you might already see, we can do a similar thing with all the other integrals as well. However, there, obviously, we should use Fubini's theorem in a different order. For example, here in the last integral, having the third component means we should integrate with respect to x3. However, this also means that in this case, we have to integrate from -infinity to +infinity. Indeed, this is the big difference. Only the first component is cut at 0, not the other ones. But this also tells us that the fundamental theorem of calculus gives us a vanishing integral here. Again, we can just use the antiderivative, but then the compact support tells us that going to +infinity or -infinity gives us 0. So in total, all the other integrals here will vanish. And in fact, only the first one remains, which is a two-dimensional integral now. So you might already recognize we are almost there. We just have to check that this one is the integral of omega over the boundary of M. And in order to see that, we have to go back to the inclusion map I. Simply because we effectively integrate I star omega. And maybe that's a good point in time to remind you what this pullback I star actually does. So what we do here is to take some v vectors from the tangent space at the boundary del M. And this is important because it's an n-1 dimensional vector space. And this one we have to embed into the n-dimensional vector space TPM. And this is done by the pullback, and the definition is not so complicated. First we have omega at the point I of P, and then the vectors are just transformed by the differential of I. So this is the general definition of the pullback, and of course the differential for the inclusion map is quite simple all the time. However, the only thing we need now is the picture in R3, and there everything is quite simple because we see the tangent vectors look like that. So the first component of all these tangent vectors is 0. Hence the input that omega gets here is always 0 and then something in the two other components. And of course the inputs here are completely given by v1 and v2 respectively. So this means if we apply I star to dx1, we always get out 0. And on the other hand, for all the other components, we will not change anything. In fact, this is all we need to know, because that knowledge we can apply to our omega. So no matter which n for the dimension we choose, we always know that omega is given by such a combination where in the forms here at the back, always one dx is missing. Therefore, I star omega will cancel all of them except the one where dx1 is missing. This is the only one that can survive, and there our integration will happen. So here we integrate over the boundary, which is a two-dimensional manifold. In fact, here we can write it's 0 times R2. And translating that to an ordinary two-dimensional integral gives us the following. By definition, the first component of f1 has to be 0, and we integrate over x2 and x3. And that's already it, because this is the same result as we had it for the first integration. In other words, we have proven Stokes' theorem for the case of the half space. And as already mentioned, nothing really changes here in the proof if we go to a different dimension n. In fact, every step here in the proof works even in the case that the wedge products are much larger. So please keep that in mind, because with the next videos we will extend this proof to manifolds as well. So really hope we meet there again, and have a nice day. Bye bye.